Hello, let's talk about what we've seen so far. And we know that from a historical perspective, the concept of computer programming has been used for different projects in science and engineering. For example, the moon landing project. In fact, when you go to NASA, either in Houston or Florida, you'll see part of the computer system, the hardware, in their museum, showing what they used to land on the moon. And it's interesting because those computers are less powerful in terms of RAM and operations per second and many other concepts. Those computers are less powerful than your smartphone. So it makes you think how computer programming has evolved in hardware and software. Of course, any spatial mission will require lots of programming, probably Fortran or C++ or C. A satellite means that you have to gather data, compress data, send data, interpolate data, obviously GPS, evidently computer simulations. When do you use computer simulations? Computer simulations are used for analyzing models. Models meaning that if you were to build a bridge, right? Okay, that's a pretty unsophisticated bridge, but my point being that all these are the structural supports. And this is just one type of bridge, right? Because you have kind of like the Golden Gate where you're supported on the top. But you have this one. And the engineers would have to find the load which would be applied to the structure. So how deep they have to create the foundations and the structural support. They have to find the shear load, which is in X and Y direction. So first of all, X, Y, and Z, right? So imagine X, Y, and Z being your coordinate system. They need to find the shear load, which what happens when there's wind and different directions. Is the bridge going to be able to sustain it? Is the material strong enough when there's a traffic jam? So things like that. You want to know the maximum load, the operating load, the frequencies of the load. If this starts to oscillate because of cars going at a certain speed, this is going to have a frequency that you want to make sure is different from the natural frequency of the bridge. Otherwise, they can start oscillating pretty dangerously. Before you build the bridge, you want to make some analysis, preliminary analysis of what the situation will be. And first, you start with some simple calculations in 2D like this, with loads, where you do summation of forces and X and Y, etc. And then you turn to a 3D model using some CAD where you actually design the parts of the bridge. And then you do computer simulation, which will put the loads on places you want, and you can actually find the deformations, which are usually written as U, deformation vector. And you can find the stress throughout the structure, the strain throughout the structure, etc. Those elements are found, those quantities, mathematical quantities, are found usually using numerical simulation. Numerical simulation means that you know what the equation for the deformation of a bridge or a solid body is. You know the equation, but you solve the equation. The solution to the equation is not the exact solution. The solution to the equation is a solution found with computers which is approximately the same. Sometimes it's not exactly the same, but the numerical solution is not necessarily the exact solution. Okay, so unless, for instance, unless once you go to structural engineering and there's a column problem with a load, people know that depending on the load, this could have different types of deformations, that or like bow, like that. Different deformations the column can have. These deformations have exact solutions, and that exact solution can be programmed in a computer also, where you compute the exact solution of where the deformation is in any point of the beam or the column using computers, so that later you can use different geometries, different radiuses, different lengths, different materials, and be more versatile. But some other times when you have a complicated system, you don't have the exact solution. That's when you use a numerical approximation, a numerical solution that will tell you approximately what the deformation will be. And then, of course, engineering practice is that since it's an approximated solution, you oversize your system, you make it stronger by 15, 20%, so that the error of the solution kind of compensated by the over design of your system. Okay. So computer simulation is a big one. That's part of what I do for my research. Obviously, scanning technology for medical field is another one that you need hardware, but you also need software. You need your images to be processed, lasers as well. Of course, you need a software to create the pulses of energy that you need for your lasers. I took this from the book, and I'm not sure what they meant with this. I'll have to go back and read. So I took it as global change, meaning that programming has changed the way we work, the way we solve problems, the way humans have evolved, because it's advanced science so much. Communication skills. Obviously now we can communicate A, with more people faster, and B, there are softwares that help you convey your ideas much better, with better grammar, with better spelling. This one is a huge one: design, process, and manufacture. With design, you have something called CAD, which is modeling software. Process, you have control theory. In control theory, you have different schemes that will help you control a process and design a future or more evolved process. And of course, manufacturing. Manufacturing, you can think of 3D printers, mills, lathes. They all have chips that require some type of program printed on them. And analyzing is connected to computer simulation, to GPS. Analyzing is basically taking data and processing it. So like Python is a good one for this one, which we'll talk later about. Computer hardware. So let's review a little bit about what we saw about computer hardware. This is a huge aspect because this is what connects to the compiler. So you have your memory, your physical memory stick. This is your RAM, which is constantly talking to your CPU, your control unit, your control processing unit. And there's going to be some type of architecture. If you notice, there's going to be a file on your computer called x86. And you can read about this. It's not part of this course, but before x86, there were others. There were previous configurations for the logic of the processor and the memory and the whole system to be able to communicate, because they have to have the same language. So x86 is one platform that has been established for processors to be able to take commands and run with them. And at some point it's released. You can force that. You can force a release with advanced programming techniques. or you can basically let the computer decide. That's why Intel and computer and chip manufacturers and computer manufacturers like IBM and others work on new technologies to make it faster, to make it more reliable, because they build their system on top of this kind of structure to make your computer better for an application. So by now, if you want a computer for Photoshop, it's not going to be the same that if you want your computer just to run PowerPoint. Or if you want your computer for gaming, then you need some type of RAM that would let you accumulate your data and send it in a much more efficient way, bits per second. And talking about gaming, there's another system called the GPU, which is your graphic processing unit. And this will do all the computations, like if you think about your NVIDIA video card, they will do all the computations for your graphical processing unit. So for instance, before, I think we talked about this already, before when they first started making computers and programming languages were developed in the 70s and early 60s, the computer screen was not there yet. It was just the CPU, the hard disk, actually it was just the CPU, the memory, and the printer. A printer that once you type something, you create your code, compile it, and once it's compiled, you would print it. That's why the very first code that you will learn when you're learning how to program is the hello world, because that's the hello world is the code that they used to use to see if the system was working once you type something kind of like in a black box, and then you ask it to print. They would say, okay, at the end, print a line, and the line was kind of like hello world established by convention, just to make sure that the system was alive. All right, so this is more or less how the hardware works for the RAM. Now, after this, you can always say save a file, and then it will go to hard disk, but that's different. Where the computation and the mathematics and all the magic of converting your information into binary and such important back and forth is right here in your processing unit. What about computer software? So we talked about hardware, how hardware requires the RAM, the hard disk, and printers and screens. And then for that, you have Windows, Macintosh, Sun, meaning IBM, things like that. And then on those systems, you can install your operating system, or called OS. And of course, you have Windows, Apple or Mac OS, Linux, Unix, and there are a bunch: Fedora, Red Hat, Solaris. Depending on what you want, you will have configuration that you will be working pretty good for you. There's another one that I really like, which is SUSE, OpenSUSE. If you want to look it up, if you're like installing Linux-based software, you should try this one. It's OpenSUSE, S-U-S-E, OpenSUSE. It's a really good one for Linux-based software. The graphics are very nice. Then you have your application software, or what's called the application programming interface, the API. And then you have your compilers, your word processors, kind of Microsoft Word, your spreadsheets, kind of like Excel, etc. Your Adobe Illustrators, your Photoshop, all these applications. Same thing that PowerPoint that we use on top of your operating system. And then you have the users. The users are us, students, professors, engineers, lawyers, etc. So this is the circle of the computer. One side is how the model of the computer evolved, and here are the examples of what's currently the case. We also mentioned there are different programming languages, and it's called languages because they kind of use different ways of expressing the same idea. So, for instance, English, you say tree, right? So a tree, well, that's a type of tree, or like a tree like that. There are different types of trees, but we kind of said, okay, anything that is like that will be a tree, and to make things simple, we'll just say tree. Now, there are different types of trees, but that's a different case. What we're trying to say here is that that object in the world in English is called tree. In Italian, it's called albero, and Spanish is called árbol, etc. So the same concept could be having a different syntax and a different way of representing it in different languages. So in C++, you would do your area like this with a semicolon at the end. C is based on C++. You will be pretty much exactly the same. Remember that the difference between C and C++ are pretty subtle. And MATLAB is based on C++, so you can also express it in a more compact way, where this operator is the power. So 2 to the 2 is power. Fortran is formula translator. This is in Fortran the same way that in Python. This is 2 power to the 2. So this is how you write area in Fortran. ADA, this is pretty similar to Fortran, Java, Scheme, Basic, etc. But in terms of cloud computing, you can have a tablet or a phone, and you can connect to what they call the cloud, which is a bunch of servers and clusters of computers with huge amount of RAM and disk and pretty advanced processors, where they would perform all the computations for you. They will have compilers, they have application program interface, they have a bunch of stuff on their systems, and their systems could be in Seattle and connected to other systems in London. So their physical systems run 24/7, and even if the power goes out, they have backup systems to keep them running. Because picture the power goes out in San Francisco, and then you're using YouTube. Well, if their power goes out, then YouTube wouldn't work. So that's why they would also have independent power connected to the clusters, because the cloud is supposed to be living, is supposed to be alive 24/7. So for instance, a basic difference is that Ansys is one of the companies that I actually use for cloud computing. There are a bunch of them, Penguin and others. So as I said, I have 2 8 CPU cores in my local computer versus accessing their cloud, about a couple of $100 per year. I have access to 132 CPU cores for my computations. The RAM's the same thing. So in my case, I have 24, but it's pretty common to have only 8 in a single computer. For a cloud computing platform for scientific computing, you get up to 1,000 gigarams. So notice the difference between 8 and 1,000. That is quite a lot. In a local computer, you probably only run one task, because if a big task will take your whole memory. Like if you're editing a video with Adobe Premiere, you know that when you render it, that could take all your RAM, and when you open a PDF, kind of stays there for a while. Cloud computing, you can do a bunch of jobs and tasks at the same time, because they have such a powerful system. One task could take up to 8-10 hours. I have problems that take 5 days to just get me a solution not even knowing if that's going to be the correct solution afterwards, versus 6-day task in my local computer could take only 6 hours on the cloud. So, of course, right now you probably don't need the cloud other than to save pictures or videos, unless you're already working on engineering projects. But later on, when you have to back up data or you need a bunch of processors and RAM, you would probably look into the cloud for that. So in Texas, we have what is called TAC, which is the Texas Advanced Computing Center, and this is in Austin. Is a UT system platform. So if you go to any of the UT universities in San Antonio, El Paso, in Dallas, anywhere, Arlington, you have access to. You can create an account to access their cluster, their servers. Back when I was doing my master's in mechanical engineering in 2009, this was the second biggest cluster in the world. The first one was a joint effort of the European Union. I don't know which one right now, might be the 5th or 10th. I don't know. 10 years ago was a huge deal. But yes, this is the cluster TAC in Austin. And they have a huge visualization wall, which is this one right here. This wall is for visualizing and computing weather predictions and weather tasks that need to be performed with a huge amount of computation power. So that right there is also an Austin facility. And the way they cool the computers, so actually a whole room is dedicated only for the cluster. So they have their own power, they have their own cooling system with air on the floor and with water through hoses cooling down the surfaces of the components. Of course, the water is contained. You don't want water leaking everywhere. The water is cold temperatures flowing through the cluster to cool down the system. So we have different links that we should be able to see. So if you click them on your PowerPoint, you should be able to see more information about the clusters. And in terms of data storage, we also talked about this a little bit. We mentioned that there are different types of variables. We have the int, the float, double, string, or characters, and so on and so forth. And for int, we said that we're going to have allocation in memory, where the chain of zeros and ones will correspond to natural positive and negative numbers, or signed and unsigned. And one thing is the actual number, and another thing is the address. So the RAM, the CPU will have to compile and convert your plain text and numbers into binary instructions, an assembly code, and then translate your words and numbers into binary. At the same time, is saving them locally on your hard disk or in your RAM as well. You're saving information on your RAM temporarily for allocating it later. So the processor knows where RAM is allocated temporarily, so you can later on open it and access it, and what the information means. Now, if you decide to save this to a file, then goes from RAM to your hard disk. That's your hard disk, which is solid state disk or whatever technology you have on your computer. Computer programming is often used for solving engineering problems or scientific problems as well. This is using computer programming to implement the solution to problems in engineering. And the first step for doing this is being able to state the problem clearly in steps. This is to design the algorithm such that if the problem is located at a certain stage or a certain point where you have to design a refrigeration system or some type of controlling mechanism, there are going to be different solutions that you can take to get to the point. But some solutions might take more money, more time, more effort. So this is, say, the solution, and this is the problem. And this path is basically the path that takes you to the solution. So it's going to be by steps. Say that manufacture material, assembly material, or assembly parts, and your solution is get the refrigeration system done or the computer finished or whatever product or service you're dealing with. Versus this one needs, you need to buy a fixture to machine your part. Then you also have to buy the material, and then you have to outsource the material for welding. Then you have to receive it again for assembling. So the steps and the way you link the steps for between the problem and the solution is what we call the algorithm. And the algorithm is, obviously, the idea is to optimize to the minimum amount of steps for the maximum efficiency. So this one will probably take less money, less time, less effort. Maybe you need more resources, more people, but this one will take more time, more money, more effort. So the key is to state the problem clearly, and this part sounds easy, but believe me, that is not easy. It's one of the most complicated parts because you have to understand the problem. If it's a compressor, you have to understand the physics of the compressor. If it's an airplane, you have to understand the physics of aerodynamics. So understanding the problem could be pretty complicated. It might take a long time. The second step for solving engineering problems is describe the inputs and outputs for the problem. So what are the inputs for making an airplane if we're in the business of making airplanes? We need aluminum, and we need material, we need turbines, we need a bunch of controls and a bunch of circuits. So what are the inputs? A lot of inputs. What are the output? The airplane is the output. Same for your program. The inputs are information, or the input is a database, or what is the output? Is the output an action that the controller, that a robot is going to perform, or is it manufacturing a part? So define the inputs and the outputs. The third step is work the problem by hand or by a calculator, so that, as we saw before, talking about the example for bridge and structures, you start with simple calculations for understanding the problem, the magnitude of the problem, if it's the size is in meters versus if it's kilometers, meaning if it's 10,000 times larger than you thought, if it's going to be 10,000 times more expensive than you thought. So the key is to start with Excel or even programming your solution first by like this, using the algorithm. When you translate this algorithm into actions, say, take the number of inputs and calculate number of outputs. This kind of thing is called a pseudocode because you're calculating by hand the steps before you program them on your using C++ or Python or whatever language you use. So make sure that you take some time to implement a logical solution with algorithms and pseudocode before you jump into the code. Because if it's not clearly defined, you will confuse yourself pretty soon, pretty fast. Fourth step is develop a solution and convert it into a program. So if the solution is manufacturing, perhaps you need a language or a system that will take your solution. So maybe Python wouldn't be the best option. Probably assembly or C++ would be a good one. If the solution is a website, then maybe HTML would be a good one, or um, or perhaps the if the solution is processing data, but you don't need to do it in a very complicated and fast approach, maybe Python is a good one. So depending on what the output is, you choose the language. So it's not necessarily, I know one language, I'm going to use it for everything. No, because languages are designed for different applications. And the last step is to test the solution with different data. This is called the validation. So if your data works for aluminum, say you have your airplane and you're studying how to the formation, how's the wing deforming with different altitudes and different velocities. So make sure that and this is something that is done. Make sure that you use different velocities for the wind, so different wind velocities. So not only one set of data. Make sure you use different wind velocities because the airplane is going to work at different conditions. Okay, so the 5 steps are understanding the problem. So for an airplane, will require a bunch of small problems that will come into a big problem. Then describe the inputs and outputs. What is it that we need? Is it that we are trying to manufacture the airplane, or is it that we're trying to create a reliability concept of how strong are the wings? So make sure you can focus your energy in the actual problem. So describe the inputs and outputs of the problem clearly. Work the problem by hand. So like here, you can try this. You can study this as a beam, where the beam deforms depending on different loads, and then you can program that and then add to the program to make it more complicated and closer to reality, and then develop a solution and convert it to a program, which is what we're saying. Once you have your model, which this is your model, your 2D model, you can create your 3D model, and once you're comfortable with the model, you can turn it into algorithm for programming it. And then at the end, when you have your code working, you need to use different sets of data to validate your code. And comments are very important because, as we said before, most of times codes are not only designed for one person to work on it. If you work for a company, you will work on codes that other people wrote. And one of the comments at the very top is going to be the version of the code. There's going to be also who has been working on it, what dates. So that's introduction. Other important comments are what some lines are supposed to do, because sometimes it's pretty hard to figure out what the code does until you go in details and start printing stuff and debugging stuff. So to save time and effort and energy, you put comments to say from lines 12 to 24, we read a file and change rows or whatever. So that's why comments are very important, because you let other people know what you're doing, or because if you open a code that you worked on 5 years ago and you need it again, then you can go and quickly find what is it that the code was doing, or what part of the code is that you really need to change for your new application. This part we said is not comment. This part is the hashtag include, is to call headers and libraries that your code will need so that you don't have to reinvent the wheel. So if you want to print to your screen, then You can use the input-output stream. If you want to use square root or absolute value, then you can use the C math library. If you want to use the standard namespaces for classes and functions, then you can use standard namespace. So those things are for the compiler to know that you're going to be using functions that are specific to your code. For instance, if your code, if you don't need to use square root in your code or absolute value or exponential equations, then you don't need to use CMath. Talking about inputs and outputs, we can see one example here where you want to find the distance between 2 points. And this is applicable for many fields, aerospace, manufacturing, and this is a crucial problem, even though it's very simple, but it's important to know because in manufacturing you have tolerances. So if you, for instance, you want your diameter of a part to be 3 inches, so you need to have somebody use a mill or some manufacturing process where you go ahead and remove material until you get to 3 inches. You could have started from a 3.5 inch rod, and then you start removing material, but then you need to have a routine that tells your machine how close to the 3 inch mark you are. So the precision of that distance will prove your manufacturing process to be successful or not, and the diameter be manufactured correctly. So let's say you want to find the distance between 2 points. The inputs would be the information needed for point 1. That information could be the X and Y and Z point locations, and then obviously the information for point 2. And then if it's only 2 points, then you're going to find the distance between those 2 points. Your code is going to compute the distance, and then the output is the actual distance between the points. So in this example, you have 2 points, one located in using X and Y, one located at 1 and 5. So right here. And the other one is located at 4 and 7. So 1, 2, 3, 4, and 5, 6, 7 here. So a point between 1, 5, and 4, 7 is this one. And the way you calculate that is with the square root of site 1 plus site 2, where this is site 1 and this is site 2. Site 1 is computed by x1 minus x2. So, x2 minus x1, 4 minus 1, and y2 minus 1, y1. So 7 minus 2. It will give you 3.61, could be inches or meters or whatever distance unit you're using. And we're going to use our C++ compiler. It's a new file, and as we said before, we're going to need to include our CMath library. So let's do our usual suspects, which is include input-output stream. Then we're going to include our CMath, and then we're going to use our standard libraries namespace using namespace standard and our main function. Where we're going to return 0 for successful compilation. Alright, so now we're going to declare our variables. So let's use double for that. We don't need to have a terribly precise area for this example, so let's do double x1 equals 0, well, actually, no, it's x1 equals 1, y1 equals 5, x2 equals 4, y2 equals 7. We're gonna have side 1 equal to 0. Well, the example is not initialized inside 1, so it will be initialized as a random memory location, which is fine. As long as you declare your variable, then you're okay. Distance is the other variable that we're going to use. And then we're going to do side 1 is equal to x2 minus x1, and side 2 is equal to y2 minus y1. Perfect. Distance is equal to square root of side 1 times side 1, which is side 1 squared, plus side 2 times side 2. Alright, and then that's all we need to do. Then we're going to output our the distance is, we're going to output our variable distance, and then it's going to be distance and end of line. Okay, this should work. Let's see. We need to save it. So distance calc. Oh, except for this part. Run it. Okay, so the distance is 3.6. Excellent. Notice that if you didn't declare a variable, you would get an error that the side 1 is not declared. So that's why you need to declare them beforehand. All right, from here, I also want to tell you that you could have saved the trouble of computing distance and, well, save the trouble of declaring distance and just outputting here the computation, which is this, and that should work as well. Right, but the example from the book tells us to do that. Now, from this example, we can practice something else as well. So let's say that we want to do everything here is going to be declared randomly, so whatever space in memory that it's taking, it's okay. It's not going to be 0, but we will declare it later. So what we need to do is see out a bunch of times. So let's say here, let's say, please input x1. This is the coordinate, right? And then we're gonna say in, take it to x1. And we should do the same for everything else. So please input y1, and that is going to be taken to y1, x2, and take it to x2. Oops, x2. It's in 2D, not 3D. And y2, and y2. Okay, now if you should do that, you should be able to do it as well. Okay, when you run it, we said that x1 was 1, enter. Y1 was 5, enter. X2 was 4, enter. Y2 was 7, enter. The distance is 3.6. Okay, excellent. So these are several ways to deal with computations, declaring your variables, asking for information, you declaring your variable at the initialization stage. So in that case, depending on what the problem is, you have different possibilities to solve the issue, either by asking information or you read a file, which we'll learn later. So I'll post this example. So as we saw in the example before, the input and output from the standard libraries are pronounced cin and cout. And these are standard libraries from the C++ IO stream or input output stream. And they're very useful to print and ask for information from the user. So we just saw how they're used. You say cout. You have to use these less than doubled less than to put your expressions, your comments, your end of lines, and basically that's how it gets used. So the example was cout, then the comment and the variable, and then you can add more comments and so on and so forth. You can also use end of line, which is what we did, and end of line. And cin will input the information from the user. Some output formats are scientific. The one that we just used, which is fixed, there's right, left, so on and so forth. So for instance, let's look at this example to use scientific, which will be like this. Let's do it very quickly because it's very simple. So for that, we just need to say the same thing. Actually, I'm just going to copy it from here. But I don't need the CMath anymore since I'm not going to use any square roots or absolute values or anything. What I'm going to use is the standard C library for inputs and outputs in the flag fashion, which is this guy, for scientific and left, fixed, etc., which we saw here that it's basically different ways of printing your data. Okay, so we need to do the same thing int main, and then we're going to start with return 0. So let's create a variable which is y and it's equal to 0.221. Okay, so when we do, we have to tell the compiler that we're going to set our floating decimal with iOS scientific. No, that's not what I want. Scientific. Yes, that should be okay. And then we're gonna say with a precision of, let's say 5, just as the example is saying. And it's gonna say precision of 5. Excellent. And then we're gonna say cout is y equals, then my variable is y, and I say end of line. All right, let's see if we have any errors. Oh, cout flags. As I do have an error. Okay, so include CS Studio, that's the library that I need to include, and then C out set F iOS scientific. Yes, what seems to be the issue here? Return 0. Interesting. Am I not spelling something correctly? Scientific. Let's see, compile it, and it's, oh, of course, the semicolon. I still forget that every once in a while. Okay, and then here we have C out of Y, and my variable, which is Y, and end of line, and you don't like C out Y. What's the error here? Return. Oh, wow. Yeah, and this is supposed to be the easy example, huh? All right, sorry about that. Run it, and yes, there you go. So we have, it's going to be scientific notation, therefore you're going to say e to the -1, and then it's going to say precision 5. So let's see, 1, 2, 3, 4, 5. Excellent. So yes, that's pretty much how you can change the format for your printing options.